So next, we're happy to invite Wei Wang, BBFT presenter of Bytom, to give a speech about BBFT consensus on Bytom sidechain. Welcome.
Good afternoon. Thanks for joining us for today's Bytom block DevCon 2. As a typical distributed system with state replication, blockchain consensus is very crucial to a blockchain network. So consensus is a set of rules that define how blockchain nodes reach a final state and how to resolve discrepancy, and sometimes in case of faulty nodes, how to enforce punishment. And in BBFT framework, we designed a new consensus framework called in Bystack framework, we designed a new consensus algorithm called BBFT, and that's specifically to power the Vapor sidechains. So this is the layered framework for the whole Bystack design. You can see that at the bottom layer sits the Bytom blockchain, and it uses a classical proof-of-work consensus. And in the second layer, Vapor sidechains adopt proof-of-stake plus BBFT. So the proof-of-work consensus provides excellent decentralization and very good security. It can resist attacks. The network will fail only if there's more than half of the computing power is compromised by adversaries. And in the meantime, the proof-of-stake consensus more tailored towards performance, and the network will fail if more than 1/3 of voting power are compromised by adversaries. So why we need another consensus besides the proof-of-work? Shouldn't proof-of-work alone save the world? So proof-of-work is great in many aspects. It exists since the very beginning of blockchain. However, more and more criticism has been expelled by to the proof-of-work. One major one is energy waste, because every node basically races for the longest chain, so lots of energy waste during the computation. And from technical point of view, proof-of-work suffer from a low TPS, which is transaction per second. In the real world, for example, the Bitcoin network usually average on like 3 to 7 TPS, and Ethereum is better, but only at 7 to 15. And in the meantime, a typical fully centralized network such as Visa will easily handle 2K transaction per second, and you will see a much higher number during holiday seasons. It is not impossible to increase the TPS for a blockchain that uses proof-of-work consensus. However, we have more losses than gains. Remember the simple equation for transaction per second is the number of transactions you can put in the block times the number of blocks you can produce per second. So by that equation, we can simply increase the block size, or we can speed up the block production time. However, from the graph, you can see, just for the block size increase, you see that for a block to reach the other end of the network, it would take much longer time when the size of block increase. So that imposes a very great challenge. First is a storage challenge to nodes, because now you have more transaction in the block, and the transaction size, the block size for example, for Bitcoin is already very big. So now you need to buy more storage space for just for storage, and that basically excludes lots of node from running the full node. And also, and more importantly, it greatly increases the chance of fork. So fork means that at a certain point of time, the nodes in the network, they have a different view of the final state of the blockchain. So the fork is really, really bad, and because it defeats the sole purpose of proof of work, which is fully decentralization and resistant to attack. Because when fork happens, you basically reduce the computing power of the whole network, and attacker can easily control the network by using less than half of the computing power. In the meantime, in some of the real-world use cases, especially in the enterprise business case, users are more care about performance, and especially there already some level of trust established in the network. So a user, they don't want to wait for a long time to see the transaction to be locked on the chain, or even worse, they definitely don't want to see a already confirmed transaction to be reverted because of fork. So, so I think in the end, it is a design choice of proof of work that pick the decentralization at the highest priority that makes it undesirable, especially in some enterprise and business use case. So people now proposing proof of stake as a viable solution to address the issues that proof of work cannot solve. But there are also debate between centralization and decentralization. But I think, and put that the debate aside, I think for now proof of stake is a pretty good compromise. That the performance and decentralization that can coexist. So, but why we need another BFT consensus algorithm? I mean, BFT is not a new idea. It's already, the first practical BFT algorithm was proposed in late 90s. So here you see this is the typical three-stage consensus flow in a PBFT setup. This setup, I would say, cannot scale very well in open network. It will work mostly in laboratory or private network when bandwidth latency is not a big issue, because every node needs to talk with any other nodes in this single consensus round. So the communication cost will increase exponentially to the number of nodes in the network. So in an open network, especially the bandwidth and the latency is very dynamic, and when a small increased number of nodes can easily congest the whole network and make all the consensus stall. So to solve the problem of communication cost, people start thinking about how we can aggregate the key and using the leader node as a router to route the aggregated message to other nodes. So that reduces the communication cost to a linear level. However, this also imposes another issue that the leader node pose a single point of failure to the whole network. How about if a slow leader or a faulty leader start to handle the aggregation and the passing messages around, and the whole network can be compromised. So giving different approaches and improvement to the BFT consensus, we designed the BBFT as a consensus framework, not just a single algorithm. So we want it to be flexible to adopt further improvement or further technical and advancement. So here are some big words here. I don't want to read it out for now. So, but in specifically, the BBFT framework is a integration of dedicated proof of stake with BBFT consensus algorithm and a proper slashing mechanism that punishes faulty nodes or those wrongdoing nodes. So the BBFT had three modules: the signature aggregation, P2P communication, and network partition. We designed the module to run mostly independently with each other, and they talk through a well-defined a set of interfaces, so that because we want them to be future-proof, that if there's a if there's a better solution coming out in the near future, we can easily plug into the current model, and that still works. So for the key aggregation part, for the signature aggregation part, we right now we use BLS key aggregation. So the BLS key aggregation has some really nice properties. For example, the aggregated key size is almost constant regardless of number of keys being aggregated. Also, you can always verify the aggregated key no matter how the order how the key was being aggregated. So the order does not matter. And also the verification time is linear when the message being verified is the same among all nodes, which is just the case for the Vapor. So and for the network partition, first we abstract the network topology into a graph, in which the nodes, the graph nodes are the consensus node in the network, and the edge weight is the quantitative view of latency and bandwidth. And from the graph, the network partition module tries to find the optimal communication path between nodes by finding the minimum spanning tree. And so now we have nodes that sits at the leaves or non-leaves. So those non-leaf nodes are now called gateway nodes. And so besides doing the normal voting process, they also do a routing and a key aggregation. So the purpose of network partition is to optimize the network communication in a real-world setup. For example, if you have nodes running in different continents, say United States and China, and you certainly don't want lots of message passing around across the ocean. So we try to minimize the the message passing along this slow communication path and optimize within a very fast or more localized network. So as a quick, simple example, suppose we have five node network, and the 5 nodes have been partitioned into 2 levels. The top level are G0 and G1 nodes, and the lower level are C nodes. And so the lower level nodes are only talks to its intermediate upper level node. So the first C node only talks to G0, and the rest 2 C nodes only talk to G1. So beginning, and also the leader node at this round is G0. So G0 start to propose a new block and send to its peers at the same level, which is G1. Now, G0 and G1 start to passing down the message to its lower levels until all the nodes has the proposed block, and this stage is called the distribute stage. Then the nodes start to cast their vote and passing the votes along with the signature up to the higher nodes, and in the meantime, along the way, those gateway nodes, which is non-leaf nodes, collects the message receiving from children and aggregate the messages and passing to the upper level. And the very top level, those top level nodes, they will do a peer-to-peer communication to have the complete set of signatures of all nodes. This is called aggregate stage. And finally, the aggregated message then passing down along the path until reach all the nodes again. So this is called the finalized stage. So let's see some numbers. The total number of messages passed around in a single round is in the order of a square of number of top-level nodes. If we constrain the number of top-level nodes to a square root of total number of nodes, then we have a communication cost within the linear complexity of total number of nodes. And at special cases, when the number of top-level nodes is the same as the total number of nodes, we have exactly the same configuration as a practical BFT, PBFT. And if there's only one top-level node, then we have a FBFT. And our internal benchmark shows very promising numbers. We can reach up to 20K transaction validation per second. And the confirmation time on average for a transaction is 0.6 seconds. And the possibility of fork is very low and only at 0.27%. So I think those numbers are very promising. And for now, we have the draft version released on GitHub. And in our released Vapor mainnet, we have a very simplified version of BBFT implemented. If you want to look at it, if you want to see it, you can also download it from GitHub. And of course, this consensus framework is there are still details to be left to be figured out. For example, how to do proper slashing and how to find the defaulting nodes. And that's the direction we're still going to pursue. And of course, we're open to suggestions from the community, from other peers. So, thank you.